In this video, we're going to continue our work on section 2.8, curve sketching, by looking at example 2. So in example 2, we are given a function b that is the company's bank balance. And this is a function b of t, where t is the number of weeks after the company has released a new product. And the function is given in the graph on our notes. So what we want to do is sketch a graph of the marginal balance, where we are told the marginal balance is the rate at which the bank balance was changing over time. So just to summarize here, if B is the graph given, so here's B, we want to draw the function that is the marginal balance, which we are told is the rate at which the bank balance changes over time. So that would be the derivative b prime of t. So first, let's look at our function b to see if we can find some of the critical points. And why are we concerned about finding the critical values of b? Well, we want to get a sense of what b prime looks like, so the derivative of b. And so to do that, we might want to find, well, where is b prime equal to 0? And those are exactly those critical values of our original function b. So let's first ask, where is b prime of t equal to 0? So please take a moment to pause the video and see if you can identify on this graph of b where the derivative is 0. That means, where do we have a horizontal tangent line? Awesome. So you should see that we have a horizontal tangent line here and here at this little min and max. So I'm going to highlight those points or label them. So what are those t values for those zeros of the derivative? We see one is around 1/2. So we have b prime of 0.5 equals 0 and b prime of 3 equals 0. So we know at those 2 points, if we're drawing our sketch of b, we know at those 2 points our derivative is at 0. So then what happens to the derivative on the intervals that are sketched out by those 2 zeros? So reviewing this table here, we see that we can find information about whether or not our derivative, f prime, is positive or negative, and if it's increasing or decreasing based on just the behavior of f. So first, let's determine where f prime is increasing or decreasing, or rather, f prime is positive or negative. So those values, or the first derivative being positive or negative, depends on where our function is increasing or decreasing. So if we set up a little table for ourselves, we see that, well, our original function b, and I'll use green to be consistent here, our original function b is decreasing on the interval from -infinity to 1. So if we just start from anywhere down here, we actually start at t equals 0. So our b decreases from 0 to 1/2, increases from 1/2 to 3, and then decreases from 3 to positive infinity. So let's keep track of that. So on the interval 0 to 1/2, use decimals here, 0.5. What's happening to b? B is decreasing from 0.5 to 3. D is increasing. And from 3 to positive infinity, our function is decreasing. So what does that mean for our derivative, b prime? Well, that means b prime, when our original function is decreasing, b prime is negative. Increasing, b prime is positive, and decreasing, b prime is negative. Okay, so we just took care of where the derivative is positive or negative. So negative down here, positive on this interval and negative again here. But now we want to know, is our derivative increasing or decreasing? Again, just going back to this table, we can find whether or not our derivative is increasing or decreasing based on the concavity of our original function. So let's take a look and identify the concavity of our original function. So where are we concave up? Here, right? And so where does that concave up change to be concave down? Tell me when to stop. Should I have stopped? Yeah, maybe around here, huh? So let's call that about 1.5. So we see that we have a concavity switch at 1.5. And then what about as we continue, we're concave down until where? Maybe I should have stopped. Maybe about here. So about, we're just estimating here, about at 6, let's say. So now we have some more information about our function B, and then some consequences of what that means for our derivative B prime. So we know on the interval from 0 to 1.5, our original function B is concave up. On the interval from 1.5 to 6, our function B is concave down. And from 6 to positive infinity, our function is concave up. So what does that mean for our derivative? Well, whenever we are concave up, our derivative is increasing, concave down, decreasing. So here where we're concave up, our function is increasing, concave down, decreasing, concave up, increasing again. So that means if we look at each of these chunks of intervals that we've made, so a chunk here, chunk there, chunk here, we can draw that behavior of our derivative. So what's happening on this first interval? Well, from 0 to 1/2, we are decreasing, and we're also, we're negative in our function. In that derivative function, we're negative, and we're also increasing. So f should look something like this. And then from 0 to 3, we're positive, and we're also increasing until we reach 1.5. So we're increasing until 1.5. From there, from 1.5 to 6, we're decreasing until we get to 3, we get to 0. And then we continue to decrease until we reach 6. And then we start to increase again. So to summarize here, we had several important points that we were looking at to graph our function. So those points were 0, 1/2, 1.5, 3, and 6. So what we've done, I'll label 1.5 or 0.5 and 0. What we've done is determined the behavior of our derivative of on each of these smaller chunks. And we've done that by looking at whether or not our original function was decreasing or increasing, and whether or not our original function was concave up or down. All right, great work, everyone.